Seal strength testing and seal requirements are topics that are very important to medical device packaging. And it's also one of the topics that I have a passion for and have discovered that it's a passion of many other people as well. And it can be very challenging for new people and engineers in the industry to figure out what to do when it comes to seal requirements and development. So in my experience, I think that's because there's a lot of misinformation and little guidance on the topic. This starts with the mythical 1 pound minimum seal strength requirement. And for these reasons, I have been leading the crusade for education and change in the industry with the support of many people from medical device companies, other converters, and packaging suppliers. And I'd like to thank everyone for their support, especially the ASTM task force members who have been key in helping to develop a guidance document. With that being said, for over 30 years, people have struggled and been confused and challenged with the 1 pound minimum and seal strength. And I think that the key is that it's used and perceived as an industry standard when it really isn't. And I think that eventually it becomes self-evident because having an arbitrary value doesn't make sense for all packaging applications. So 2 years ago at HealthPack, I challenged the industry that we can do better. And the overwhelming response was, yes, something needs to be done. And Geoff, you should do it. At the time, it kind of felt like being told instead of volunteering, but it's all good. No worries. This led me to present and propose a work item to the ASTM FO2 committee on primary barrier packaging. The proposal was to develop a standard for determining minimum seal strength, and there was a strong agreement and support to create a task force to work on the item. Since the work group was formed, a lot of people outside of ASTM have expressed interest and are looking for updates and guidance on this document. So my hopes for the webinar are to clarify some confusion regarding seals by addressing some fundamentals of packaging seals, to continue to dispel the false premise that 1 pound minimum seal strength is a standard or a requirement for all packages. And 3, to give an update to the development of the ASTM guidance document to the industry. So even though I'm focusing on seal strength in this presentation, I think it's good to keep in mind this perspective, and it kind of comes from one of the task force members that I've been working with, and it says that seal strength is not the only requirement of packaging seals, and for the same material may not be, or for some materials, it may not be the limiting factor for a seal. So I think that's a really good perspective to keep in mind. So starting off with the purpose of medical device packaging, which is to protect against microbial contamination. This means package integrity to the point of use is the bottom line. And package integrity is related to materials and seals, which basically means no holes in the package or channels in the seals. So let's focus on the seal portion of that aspect. When developing seal requirements of a sterile barrier system, there are 3 key elements which need to be established: seal integrity, seal strength, and seal width. So seal integrity is the fundamental aspect to ensure that the product is sterile to the point of use. Regarding seal strength, a minimum seal strength is required per ISO 11607, and a maximum strength may be necessary, especially when a seal is designed to be open for aseptic presentation. And finally, seal width. A minimum seal width is also required and to be established per ISO 11607. So how are they related? Seal strength and widths are the primary controls for maintaining seal integrity. I like to say that again. Seal strength and width are the primary controls for maintaining seal integrity. The combination of these attributes define the amount of work or energy to keep the package closed. So in physics terms, work equals force, which in this case is seal strength, times the distance, which in this case is the seal width. These concepts are captured in the concept where you can have a narrow but a strong seal or a wide but a weak seal, where either can be effective. Another fundamental that we have to cover is the confusion between seal strength and integrity. I think that the confusion is because people are focusing on the relationship versus the test methods used to evaluate each characteristic. Basically, seal strength tests don't discover integrity failures like holes and channels, but integrity test methods do. Burst strength testing is one of the most widely misunderstood and confused examples of seal strength versus integrity test methods. And the two common misconceptions of burst testing are that it will find the weakest part of the package seal, and two, that it will fail if a channel or a hole in the package is discovered, therefore becoming an integrity test method as well. To dispel the integrity detection method, I'd like to perform a burst test challenge, and here's a video that demonstrates this challenge. In this video, you can see that we're taking a three-side seal pouch, punching a hole in it all the way through both sides of the materials, mounting it on a burst tester, and then starting the test. You see, as it goes through the process, it starts to build pressure, just like normal. Actually goes and continues to build pressure until the point where it fails. So there is obviously a large hole in the package that wasn't detected through the process. So the reason why this happens is because burst testers basically generate pressure by compensating for air loss. And that's because they're designed to work with materials that are porous. So kind of segregate a little bit more too. Here are some common seal integrity tests. ASTM 1929 and F3039 are common dye penetrant tests for porous and non-porous packaging. And ASTM F2096 is a common one for whole package integrity testing, often referred to as the bubble leak test. Common strength tests are ASTM F88, which is the peel strength test method, and ASTM F1140, which we just kind of demonstrated that is an internal pressurization test as well. And to further emphasize it, the evidence that you can refer to, there are a couple of standards which classify seal strength and integrity test methods differently. And those are ASTM F2097, and ISO 11607 and Annex B. Now, as a side note, ASTM F2097 is a great compendium of test methods that are used commonly in the medical device industry. So I would highly recommend taking a look at that if you haven't already. So now let's move on to seal strength requirements by asking the question, what is required? So the most common answer to the question is 1 pound. 1 pound per inch width is the minimum seal strength. And the reason that people give this answer, I think, because they think it's a standard. Well, we're still looking for where this came from, and I think in a couple minutes I'll give you some updates on my research into this topic as well. In the end, sometimes it works and sometimes it doesn't. And it's not rational to have a universal seal strength minimum value for all packaging types and applications. Hence, the featherweight argument. And the featherweight argument goes like this. If you have a light device, like a feather, that weighs significantly less than a pound, you may drastically be over-engineering your seals or your packaging with a seal strength of 1 pound. And you're giving up opportunities for reduction of materials and or cost savings. On the other hand, if you have a heavy device or object that weighs significantly more than a pound, now the seals may be grossly insufficient to even keep the product in the package or prevent a seal breach. So in continuing to ask the question, what's the right seal strength, and figure out where 1 pound came from, we can look at regulatory, literature, and some networking that I've done to research into this. And here's a summary of the seal strength values and references accordingly. So from a regulatory standpoint, you have ISO 11607-1, which does not require a minimum value, or does not state a minimum value that is specified, but you need one, and you need to figure out what that is. EN 868 standards, on the other hand, make reference to a minimum seal strength requirement, and those all tend to be right around 1/2 pound. In literature, on the other hand, trying to research this and figure out where to get guidance on seal strength, you can look at documents like a packaging encyclopedia, medical device packaging handbook, and some patent searches as well. And these documents demonstrate that there are a wide variety of peel strengths required for different packages, all the way from, in the patent search, from 0.1, 0.2 pounds per inch width, all the way up to 1 pound. And the difference there is the difference between a bandage, which is very lightweight, for maybe a heavier device like a scalpel. And a scalpel, I mean, relatively speaking, that's considered a heavy device then. Well, these days we have much heavier devices to consider as well. My experience over the last 27 years working with many medical device packaging applications is that the actual values vary. And what varies from 0.3 pounds, commonly around 0.7 pounds, depending on packaging configuration, all the way up to 1, and as high as 3 pounds. Sometimes you need a 3-pound peel strength because you have a non-porous package that needs to survive altitude distribution, for example. So it really depends on the materials and the application. And in the end, what the seal strength that you need is what your packaging needs to survive to the point of use. So, as promised, the search goes on for the 1 pound origin, and it still continues. But here's a summary of some of the possibilities that I've collected over the years. And it starts with guaranteed minimum from material suppliers, the general version of where it comes from. And basically, from heat seal coated material suppliers, it's what they could guarantee that a material would provide as a minimum seal strength. Then, from material suppliers again, as it relates to the tear, it's more related to the tear strength of paper or paper characteristics. So in one instance, it talks about that there's a maximum of 1 pound seal strength because that's to prevent fiber tear of paper during opening of a pouch, for example. Another reference says that it's the internal bond strength of the paper that's the limiting factor and why we should talk about 1 pound. There's other references to in networking that says it's related to a TAPI committee for easy opening packaging. But reaching out to LinkedIn community and asking a lot of LinkedIn members to kind of contribute and research this as well, the feedback that I got from many of them was, hey, there were some common denominators, and in that was related to material, converters, and possibly an origin with Carl Morata, who is the head of the TOLUS organization for a long period of time and an icon in the industry. So it starts to beg the question, what if 1 pound is not the right seal strength? And then how do you determine what the proper seal strength should be? This is where the ASTM guidance document comes in. And here's an overview of what has been worked on and what is coming in the document in the future. The high level, the overall direction is going to be more of a holistic approach to seal specifications, which includes seal width, because it's really hard to keep seal strength and seal width separate, and it really doesn't make sense to have another document to address it with as well. And in general, it will follow the aspects of design control. In the procedural section, will also include common practices for determining minimum seal strength, which the methodology is generally applicable to width as well. So for the listeners who may not be familiar with design control or the design control model, here's the waterfall diagram, which is a high-level depiction of the inputs from the user needs and other design inputs, process and design outputs for verification and validation of a medical device. Well, some of the key elements in design control can also be applied to packaging. Design inputs, which translates into design specifications, and also process and design validation concepts as well. So design inputs and considerations for minimum seal strength are the voice of the customer, which are things like the package is too strong to open to control the contents for sterile presentation, or too weak, which brings in question whether the package was sealed or are the contents still sterile. Weight of the device / contents, well, we already kind of touched base on this, but basically heavy contents can be a challenge to seal integrity. And then what do I set for my in-process checks to make sure that the seal integrity will be maintained throughout the distribution? And through those design inputs, you need to consider the impact of shock and vibration testing from distribution hazards. And here's a video from one of my colleagues that demonstrates the shock on a package inside a shipper. And here's another one of the vibration. You can see that the dynamics during the process can be extreme forces on the seals during distribution testing and considerations. Another impact on distribution of the seals is the distribution hazard of altitude changes, which can stress the seals from the inside of the package outward as the package inflates. And a worst case example is non-porous packaging. And here's a video to kind of demonstrate that. There's a film-to-film package inside a vacuum or bell jar, and as you draw a vacuum on it, it simulates what happens when an airplane, unpressurized cargo plane, goes over a mountain, etc., and then it inflates the package to the point where it can have seal creep and open up and then fail because of a leak in the seals. So other considerations are sterilization effects like irradiation, degradation, peel strength methodology, whether it's 90, 180 degree supported or under supported test methods, and the effects of those peel strength values as it relates to material stiffness, for example, and other things like cost restrictions or considerations. So while working on the guidance document, here are a few of here are some experiences and contributions of approaches that are currently utilized in the industry, and I'll read these to you. Basically, a lot of the approaches are pick a value, it's arbitrary value or not, and then hope that it works. A lot of these people are very optimistic or have a get it done approach, and they're crossing their fingers and hoping it's going to work. Another is pick a value and calculate that it statistically works. A lot of times these are mathematically minded and, just have the caution that something else needs to be done. We have to do something more. Another is pick a value and then test that it works. So these people are data-driven and really rely on numbers because they don't lie. Another version is pick a value and test below it to verify it's okay. So I really like a number, and how do I make it work is the concept. And then there's pick a value and test above it, which becomes the new value because the first number was kind of scary. And pick a value and add a safety factor away from it. And that's just in case something might go wrong. Other approaches are find the edge of failure. Find the edge of failure and then set a criteria away from it. That's the break it, then fix it model. And other ones, determine what the application requires and then design for it. So let's think about this a little bit more and see what we can do to be better about it. And my favorite of all is, it worked last time, so it should work this time. And that's wishful thinking on many people's parts. So based on design considerations and inputs, and reviewing different ways that people determine minimum seal strengths, there are a few common approaches to defining seal strength requirements. At a high level, they fall into two groups, either a top-down or a bottom-up approach. The top-down starts with the voice of a customer, typically, and alternatively, the bottom-up approach begins with materials and process capability. One of these approaches is what I call the lowest value or lowest validated parameter. It starts with validated OQ limits, which produce a specific range of seal strengths. The low limits tend to produce weaker seals, and the process is allowed to run at these conditions, even though it may never run at these conditions. The low conditions include a distribution of the variation, which is encompassed when you use a risk-based sampling program to establish the confidence in it, and at the low end of the low end of the sealing window. The results, including post-performance testing, may be used to establish specification limits, which are subject to verification through performance and stability evaluations. This approach is common as a process specification, or often a bottom-up approach. So to try and illustrate this, I have a diagram to kind of walk you through it. Start with operation qualification window, and then performance testing, and then you set your process specifications typically from there. Now, if in your performance testing something goes wrong or has a problem, then you adjust your process specifications accordingly. Another variation on this concept is start with your operation qualification window, do performance testing, adjust accordingly, and then set your process window to be conservative and confident that you're not going to approach your performance testing results. The next approach is called guard banding, where you identify the maximum limits of the process inputs and outputs, and then shrink the limits with a safety factor. And safety factors like a safety margin, which is based on engineer experience or knowledge, stack tolerances of time, temperature, pressure, or other stack tolerances, process capability, and anticipated material degradation from aging or sterilization. This is also a process specification approach. And here's another diagram to try and outline how this works. So find a maximum process window. Then you adjust for process capability, for example, other safety factors, and then develop your high and low specifications based on that. Now, if you happen to have the voice of the customer, then you can adjust this as well. And the final approach is edge of failure. This is where you identify the extreme limits of the processing to the point of failure. Then design away from that failure, again considering design inputs, safety factors, to establish specification limits, etc. And this is considered a top-down approach and more of a design specification approach. Here's another diagram to kind of outline how this works. So again, go to the edge of failure, where you actually cause failures. Then move your design specification inward from those. Work with your process limitations as well, and determine your specifications based on that. And again, if voice of a customer is part of your process, then you have the capability to adjust accordingly as well. So some conclusions and things that I'd like you to take away from this webinar are, first of all, the 1 pound minimum seal strength is not a standard. 2, There are no universal minimum seal strengths for all packaging applications. 3, if you choose an arbitrary minimum seal strength, like the 1 pound, for example, please understand the consequences of doing that. Also, seal strength determination needs to encompass all related aspects of design inputs and establish confidence and be appropriate for the application. And hopefully, in the near future, we will be able to help the industry with a standard guide which will provide a framework for more reliable and defendable approaches and processes, which would be the ASTM guidance document. So, with that in mind, I'd like to thank everyone and also reach out to the audience that if the methodologies that I have presented here are different from what you have, or you'd like to share them, or you'd like to reach out to me and talk to them about them further, use the contact information below to do so. And again, additional thanks to the ASTM groups for helping support this as well.